welcome to this video in which I will be discussing the derivation and the solution for the differential equation representing the dynamic of a multi-rotor drone. As you know, multi-rotor drones are something that's everybody's talking about, and it's being used in many applications, especially nowadays in military. And I wanted to actually show you the dynamics and how we can actually simulate the solution for the differential equations of a multi-rotor drone. Now, to be able to derive the differential equation, we need to think of how and which part of this dynamical equation is actually going to be derived and then simulated, because there are different assumptions that have to be made. And in this video, I will make assumptions that we are actually going to look at the vertical motion of the multi-rotor. Now, to actually simulate the whole possibilities of all movements will be too much for a simple video, but it's actually achievable and it's not too difficult to achieve. To start with, we will have to make some assumptions for the analysis which we will carry out together. The first assumption is the drone is a rigid body. The second is only significant forces are actually going to be considered, which are gravity, thrust, and air resistance. The third assumption we are making here is the drone has perfect control over its rotors to generate thrust, i.e. The motors are considered to be perfect and generate and respond, generate forces and respond to orders as and when they come, and there is no delay or anything like that. The third is actually the effect of pitch, roll, and yaw are neglected because we are not going to take their effect on the multi-rotor in this video. In maybe a longer later video, I will be able to show you how we can actually involve the pitch, roll, and yaw into the equation, and it will make it a little bit more complicated, but it's doable. Again, it's not impossible, it's doable, and it can be solved by engineers without any problem. So, to start the derivation, we need to consider a multi-rotor drone with n rotors. You know, either n can be 3, 4, 6, 8, so it doesn't matter the number of rotors which we are actually going to use, therefore we'll just say n. Each generating thrust of Ti, the total thrust is represented by T total, is the sum of the individual thrust, and therefore we can represent that T total is equal to the sum of between I equals 1 and n of Ti. Now, according to Newton's law, the net force acting on the drone is the difference between the thrust and the gravitational force. Therefore, we can represent F net to equal T total minus mass times gravity, which is the acceleration according to gravity. We need to consider also the acceleration due to this net force, which is A, is related to net force by Newton's second law, which is F net is equal to mass times acceleration. Now, if we substitute for F net in our previous equation, which is F net equals to T total minus mg, and rewrite the equation, we see that T total minus mg is equal to mass times acceleration. Now, if we consider the acceleration, we are trying to get the acceleration, then we in the z direction, then we can write our equation as m, which is mass times acceleration in the z direction, to equal total force minus mass times acceleration due to gravity. Assuming that the drone is moving vertically, we can rewrite the acceleration as the second derivative of the vertical position z, which is the one we are looking at, with respect to time. And this means that m multiplied by the second derivative of z by the second derivative of time will equal total force minus the force due to the gravity, which is mg. Then we can say that to express the total thrust in terms of control inputs and the dynamics of the drone, we need to take into consideration the angular velocity. Therefore, the thrust generated by each rotor is related to the square of the rotor's angular velocity. Therefore, I can say that Ti is equal to kwi squared, where k is the constant related to the rotor. Now, if we substitute this in Ti, then we can say that total force is actually equivalent to k multiplied by the sum of I equals 1 to n, which taken into consideration all the motors, the angular velocities of all the motors. Now, if we substitute this back into this equation here, which is mass times acceleration is equal to total force minus mg, we end up with mass times the acceleration in terms in the z direction, the acceleration in the z direction, is equal to k multiplied by the sum of between I equals 1 and n of all the angular velocities of the motors minus the force due to gravity. Now, this is a simple derivation with under the assumptions which we have made for the dynamical differential equation. And as you can see, now we have a second order differential equation. Now, in my previous video, I showed you how to solve second order differential equation. In this video, I am not just going to use a library which is the ODE, but I am also going to use Python and Euler methods to solve this equation. So let's not waste any more time. Let's dive into my Jupyter notebook and see how we can actually do that. Now, as you can see, I have already prepared my Jupyter notebook, and I started by importing my libraries, and I'm only going to use two libraries, which is NumPy, the numerical library or mathematical library in Python, and I'm going to use Matplotlib for visualization. So now if I run this cell, then that means I should be able to use NumPy, and I will be able to use my Matplotlib also. The first thing I did in the second cell is actually define my parameters, and the parameters are going to be m, which is the mass of the drone, g is the acceleration due to gravity, and k, which is the thrust coefficient for which we are going to use, which is related to the motors. Then I am going to consider the time parameters, which is the starting time, the step, and we will start from 0, and the step is going to be 0.01, and we are going to simulate the behavior of our equation over 10 minutes or seconds, or whatever it is the time unit that we are actually going to use. So it's actually going to be 10. Okay. Now, the initial conditions, we have initial height is 0 and initial velocity is 0, and we will update these as we go on. Now, initial arrays that we need to create are for the time, and we use arrange, the function arrange, to create an array of time which starts at 0 and finishes at 10, and with the sample step is actually 0.01, which is represented by t values equal to mp, which I'm calling NumPy here, and I use the function arrange to create that for me. Then I use z values, which is the actual z direction height, and I created said that actually the first value, the initial value, is going to be 0, and before that I used the function mp0 underscore like to create the array. And if you notice in this example here, I am not just using zeros, I'm using underscore like, which means that the array, the array that I am creating, and it's going to be filled with zeros, but it's going to take the shape and the dimension and the type of data that are actually going to be in the array which we have created earlier, which is t underscore values. And I did the same for for v values. So I'm creating the z values and the v values, which are initial height and the height and the velocity of my drone. And I set the initial conditions to actually equal 0 for both z and v values. Then I actually went and created a for loop, and I used range between 1 and the length of the t value. So it will iterate over all the values which are in the same length as the t value which we have created earlier. So I am not going to miss any values at all. Then I said represented the equation which we have, net force is equal to k multiplied by v values, I minus 1 squared minus mass times gravity. Then I computed the acceleration, where it's equal to net force over mass. Then I went and updated the velocity and position using Euler method, which is given as v values I minus 1 plus acceleration times the time sample. And also for the z value, it's actually z value for that index, which is I minus 1 plus v value I multiplied by the time sample. And the last cell is actually the same as what we have seen in our previous examples, where I used matplotlib. I defined the figure size, and then I used plot, and I said that I want t value and z value to be my data, which is going to be plotted here. And then I defined the x label and the y label, and then I used title to include a title for my output. And then I used grid is true because I want grid to be included here for this output. And then I use plt.show so we can actually see the result within our notebook. Of course, as I always say, I can also add here percentage matplotlib space inline, and I wouldn't have to use plt.show. And when I run matplotlib, it will actually be shown here. So let's go through executing these. So if I execute the second cell, where I am actually defining and initializing some parameters, then I actually create my arrays and initializing them, and then I am actually running my for loop, and I'm calculating the velocity and the v and z for my velocity and position, and then I plot my result and as you can see, it actually has plotted for me the result. It's actually going from 0 to minus 80 and from 0 to 10, as you can see, and it's descending in this manner. So I haven't used the ODENT, which is SysPy integrator model in this case to solve my differential equation. I used Euler methods to actually do this solution. That doesn't mean that we cannot do the same solution using the ODENT. And in the next example here, I repeat the whole thing again, and I will show you how we can actually use the SysPy integrate model to call the ODENT function, and we can do the same solution. So to do that, I had to say from syspy.integrate import ODENT, and then in the second cell, I introduce my parameters and I initialize them. And I said the mass is equal to 1, the gravity is this, and k is the 0.1. And then I created my drone model and passed to it two variables, y and t. And then I defined what is the relation between y and v and z. And then I put the net force. As you can see, it's k multiplied by v squared minus m multiplied by g. And then I define my acceleration by saying acceleration is equal to net force over m, which is the mass. And then I returned v and acceleration. Then I went and did the initial conditions where I created a y, and there is a list here of two parameters, two float parameters initialized as 0, which are the initial height and velocity. And then I created my time array using a range, and I said it's actually between 0 and 10, and the step is 0.01. Then I introduced the solution, and I called ODENT to do the solution, and then I passed to it the model, the initial values, which is the values for my velocity and height, and then I passed to it the time array. Once that is actually done, then I went and extracted both the velocity and the z values, and in the last cell, I went and have drawn the actual z value against time, as you can see in here, and it should actually give me exactly the same result as we found in Euler method. So I am just running these cells, and as you can see, it actually gives me exactly the same solution. So what you need to understand that in both of these examples, I have solved the same dynamical differential equation for the drone, but in this case, I used two methods. One, I used Euler method to solve it in the first case, and the second case, I used the library, which is syspy.integrate, and I achieved the same result. And I expect that all of you should be able to do the same thing and benefit from this solution. Now, in my next video regarding differential equations, I will be looking at the model of a simple submarine, and I will be trying to solve it in exactly the same way, where I will solve it using ODENT, and then I will solve it using numerical integration, and see how we will be able to achieve the result. And till then, I will see you, and thank you very much, and have a nice new year.